Hey everyone, this is Dr. Davidson. I wanted to take a few minutes here and just comment on a few questions from our Canvas portion of Exam 3. There was about 5 problems it looked like more people had difficulty with even after doing the exam revision. So I just wanted to kind of go over those a little bit. So the questions that are included are questions 7, 9, 11, 22, and 23. So question 7 here is kind of a 2-step synthesis. So the first step of this includes the reaction of this secondary alcohol with phosphorus tribromide. The second step then is a reaction with cyanide. So the first step of this involves the conversion of the alcohol into the alkyl bromide. So bromide is going to substitute for the alcohol. And in this step, the substitution mechanism involves converting the alcohol into a better leaving group, and then the leaving group being displaced in an SN2 reaction. So let's take a quick look at that. So here is our alcohol. It first reacts with phosphorus tribromide. So this alcohol attacks the phosphorus and it displaces one of these bromines. That gives us intermediate that looks like this. Still has the H on it here, and phosphorus dibromide, the plus here. And then we've also kicked out bromide. So in the second step of this, bromide acts as a nucleophile to displace this whole group now, the phosphorus with the oxygen attached, as the leaving group. And so this is a much better leaving group than hydroxide is. So bromide comes into here, displaces this whole group, and this is an SN2 mechanism here. So when we get the alkyl bromide, the stereochemistry has been inverted, like this. Okay, so that's step 1. In our step 2, we're using cyanide as a nucleophile. So then cyanide is going to displace the bromide. Remember that cyanide is a good nucleophile, but it's one that's a kind of a weaker base. And so it is good even at secondary alkyl halides of doing SN2 reactions. So in fact, this is our second SN2 reaction then. This comes in from the backside, displaces the bromide, and because we've again done an SN2 substitution, the stereochemistry is inverted a second time. And we end up with an overall retention of the stereochemistry. So the stereochemistry here ends up the same as here because we have done 2 SN2 substitutions, each with an inversion. If we wanted to generate the cyanide with a wedge here, so we wanted to do just a single inversion from this alcohol to this wedge, what we would have to do is a series of steps that only inverts it a single time. So one way that we could do that is to start with this alcohol and make a leaving group out of this that will then be substituted for with cyanide. So if we converted this to the tosylate, with pyridine as a base, it's just going to sop up the hydrochloric acid that's going to get generated in this step. So we'll have our O-tosylate on here. Then we could do our substitution reaction with cyanide, and the cyanide will displace this whole tosylate. So then we would end up with our cyanide coming forward. So we can control the stereochemistry of this product by choosing the synthetic method that we use. All right, the next problem that some of you had a hard time with is the synthesis of this ether up here. So when we want to synthesize an ether, usually what we're going to do is take an alkoxide like this, react that with some type of alkyl halide. Just use a bromide here. Do an R prime to make sure that that's different than the one we have on the oxygen. And we'll end up with R on one side and R prime on the other side. So this is just going to be an SN2 substitution. So if we look at our ether, we could imagine doing this in two different ways. So if we think of this retrosynthetically, we could cleave this bond right here, putting the alkyl halide on the left. I'll just put an X, so this could be any alkyl halide, and our nucleophile, our alkoxide, could be on this side. The other way to do this would be to make the other bond, the other carbon-oxygen bond, and in this case, we would have the alkoxide on this side plus the alkyl halide over here. So these are the two possibilities. If we look at the rest of these choices down here, we'll see that a couple of them don't really follow into this pathway. So for example, this one here, so what sodium hydride does is it deprotonates the alcohol to form the alkoxide. So in the first step on this one, we generate O-, but when we react that with another alcohol, all we can possibly do here is acid-base chemistry, because hydroxide is poor leaving group. So this second step won't work. The bottom one takes the acidic approach. So in this case, we treat this alcohol with an acid. So in that case, what we'd end up with is a protonated oxygen over here. So this is making a better leaving group. But if we added in this alkoxide, again, all that would happen is this is very basic. It would just pull a proton off of this, and we would just get acid-base chemistry. No substitution. So this one won't work either. So the top one falls into one of those reactions that we did. So the first step, we'll deprotonate this to make the alkoxide. So O-, if we have O- here, and then this would come in and do a substitution. So we have here a primary alkyl halide reacting with this alkoxide nucleophile. The other possibility is this third one. So we just saw in the previous problem that the first step would form the bromide, and then we would have the reaction of this alkoxide with this secondary alkyl halide. So this can do a substitution reaction, but the problem here is because it's such a strong base, it can also do an E2 substitution, which may be the main reaction that takes place. So if we're going to choose between these two, it's better to choose the one that has the less steric hindrance on the alkyl halide, because that's the biggest controller of SN2 substitution reactions. So this first choice here would be the correct one. The third problem is this epoxide ring opening reaction. And so this is being done under acidic conditions. So in the first step, what happens is that the epoxide oxygen gets protonated with sulfuric acid. And it's going to make this oxygen into a much better leaving group, like this. So in the second step, we have methanol is going to act as a nucleophile. And epoxides have 2 carbons, at which point the reaction could take place. So the nucleophile could either come here to the less substituted side or to the more substituted side. But when we're under acidic conditions, the nucleophile is going to come in to the more substituted side. So it's going to come into here and open up this epoxide ring. So even though it's a highly substituted position, it's this carbon that bears a little bit more delta plus, and so that's what draws the nucleophile in there. It essentially follows an SN2 substitution, so the stereochemistry of that position is going to be inverted. So we can draw this in a couple of different ways. So if we want to draw it as an inversion, then we would have this. We have an OH left at this position. We'd have our OCH3 down here. And because this gets inverted, the methyl group stays as a wedge, and the ethyl group has a dashed line. All right, so we have to figure out which of these products or which of these answers matches this. So most of them are all drawn with, well, we can see that, okay, this is not right because it's a diol instead of an ether and an alcohol. This one's not right because the methoxy group is on the less substituted side. And so we have 2 possibilities which just differ at the stereochemistry of this chiral center. So both of them have that methoxy group pointing up. So let's convert our answer to that same format or same type of drawing. Let's rotate around this bond. And so I'm going to draw this OCH3 going up. When we rotate it, this ethyl group that's in the back is now going to end up in front because we rotated it by 180 degrees. And the methyl group that was in front is going to rotate to the back. So the methyl group is in the back. Okay, and let's compare. So this one is the same as this one. The ethyl's in front and the methyl is in back. Okay, so this turns out to be the correct answer. The other way that we could do this, if we just know that, this is an inversion, we could just, and we see how those are drawn, we could just draw it like this, and we could just put our OCH3 up here, and because this is an inversion, we would just switch the positions of these 2 groups, okay? Inversion. Okay, so this is the correct answer because it gets inverted at that position. All right, the next one is this reaction sequence here. So let's take a look. So in the first step, we're using bromine with water as a solvent. So let's just draw what happens down here. Okay, in the first step, the double bond reacts with bromine. Okay, so the double bond attacks the bromine, we lose bromide, and remember when we use Br2, this closes back up to form a bromonium ion. And I'm going to draw this. Let's see, which way do I want to do? Let's draw it with the methyl back and the bromine coming forward. The water then acts as nucleophile. It outcompetes the bromide that gets produced in that first step just because it's a solvent and there's just so much of it around. But like in the epoxide ring opening under acidic conditions, what we see is the water comes in at the most substituted side of the bromonium ion and opens this up in what is an SN2 step, really. So the OH, this water molecule, is now on the backside. The methyl group has been flipped up, and this bromine is over here. Okay, so notice that the water and the bromine, these are anti to each other. The bromide or another water molecule, we could draw it either way, can then deprotonate this water molecule here. We could have either of those to form this species here, which has a halogen and an alcohol, and so we can call this a halohydrin. Now, these are anti, so in the next step, what happens is we treat this with sodium hydride. Remember, sodium hydride is a strong base, but it's not nucleophilic. So we have hydride here, and what it does is it deprotonates the alcohol to form the alkoxide. I'm going to switch this methyl over to this side. And now, because the oxygen and the bromine are anti to each other, this oxygen can come in from the backside and displace the bromide. So this is another SN2 step. And we end up with an epoxide that looks like this. So notice that this oxygen here is on the opposite side of what the bromonium ion was. Now the last step here is the reaction of that epoxide with methoxide. So now we have a strong nucleophile, a basic nucleophile. And so we already know that when that reacts with an epoxide, it opens up the epoxide ring from the less substituted side. So this will come in this way from the top on the opposite side of the epoxide and open up this ring. So the new methoxide is coming in from the top. The ring has been opened up on the bottom, so it's O minus, and here's the methyl group. And then there's just one last step. I guess this isn't really shown here, but we'd have to have either some alcohol. Usually when we have methoxide, we have some methanol in there as well, or we could use water, and this gets protonated to give us our neutral product. So there's quite a bit happening in this short reaction sequence. The important parts here are that the OH and the methoxy group are anti, right? And that the methoxide, the last nucleophile, is on the less substituted side. So which one does this match to? Not this one, because that has the methoxy group on the more substituted side. It looks like it matches, this one right here. Right, this one has two methoxy groups, so that's not right. And this one is backwards. This has the methoxy group on the more substituted side. Inverted that. Okay, so I've got one more that was a challenging one for everybody. This is also as a reaction sequence, right? So we're going to be seeing more of these, and we're going to have some of these on the final as well. Okay, so what we're doing here is we're starting with this terminal alkyne, and we're treating it first with sodium hydride. So I'm just going to draw this as H minus. Okay, so the first thing that happens is it deprotonates the terminal alkyne. And it makes this anion, which we usually refer to as an acetylide anion. Remember, acetylene is just the smallest alkyne that we can have, 2 carbons and 2 hydrogens. All right, so acetylide is a strong base, and it's a good nucleophile. So if we treat that with this alkyl halide, right, this is just a primary alkyl halide, and so it's good at doing SN2 substitutions. So this gets substituted like this. And what we do is we extend out the carbon chain. So this is one of the best ways we have so far to make a longer carbon chain, which is really important in being able to do a synthesis of different molecules. So that's what these 2 steps are for. Then the second step, notice we have sulfuric acid and water. This is just going to be a hydration reaction of an alkyne. So we're going to add an OH at one side and an H at the other side. And remember that we get an intermediate where we add an H here and an OH here. Right? So this is called an enol because it has an ene, it has a double bond, and ol, it has an alcohol. And remember that enols tend to isomerize or tautomerize to their keto form, like this. All right, and so if we look at the answers here, it looks like this is the correct answer. So it doesn't matter in this case whether the OH goes to the carbon I showed or to the other carbon because we have a symmetrical molecule that we're doing this reaction on. All right, so those were the most challenging problems. I hope this helps. Didn't really end up as short as I wanted, but if you have any more questions, just let me know.